Algebra 2. Today we're going to look at section 4.8, which is on complex numbers, and complex numbers are tied into imaginary numbers as well. So the first thing I'd like you to do is, in your notes, just go ahead and draw a Venn diagram. We have 1, 2, 3, 4 boxes, small to large, and then a single box here. Complex numbers are numbers that have a real part and also an imaginary part. When you see the word complex, it means that you're going to have they're written in the form a plus or minus bi. And so the a part is the real part. This is real. So it can be any real number, any number that you're used to seeing. And then the bi part is the imaginary part. Imaginary numbers always have a lowercase I attached. When you put an imaginary number with a real number and either put a plus or a minus sign between it, that's called complex. Back to our Venn diagram for a minute. This comes from Algebra 1 when you first learned subsets of numbers or sets of numbers. The smallest box is N, stands for natural. Natural numbers are numbers that start at 1 and continue in the positive direction forever, but they're nice whole numbers. So 1, 2, 3, 4, 5, and so on. The next set you learned from Algebra 1 was whole. Whole numbers are numbers like 0, 1, 2, 3, and 4, and so forth. So natural numbers start at 1 and whole numbers start at 0. After you learn the idea of what a number was and then the 0, you then learn negative values. Negative values are integers. Integers are numbers like -4, -3, -2, -1, 0, 1, 2, 3, and so on. It continues in both directions on the number line forever. Then you learn about fractions and decimals. Fractions and decimals are the rational set. Numbers like 1.2, numbers like 5/8. These are rational. Repeating decimals also belongs to this set. Remember from the past you draw a little bar over top the number that repeats. So this number would be 1.4444 forever. And then over here in the box that is kind of isolated to itself, these numbers are called irrational numbers. And they are opposites of rational. And so irrational numbers are numbers that keep going forever, like decimals that are very messy, they never stop. Numbers that are unpredictable, like pi, 3.14159, and so on. Square root of numbers that are not perfect squares, like the square root of 2 or the square root of 7, so forth. All these are irrational because, again, they're numbers that cannot be turned into fractions. They're messy decimals, decimals that do not stop and do not repeat. They're very unpredictable. You don't know what the next digit will be unless you had the help of a calculator or a computer. This is all the real number system, and I started with this just to kind of tie it back to all the numbers you have been used to your entire life. Natural, whole, integer, rational, irrational, and real. And then over here in a totally different world are the imaginary numbers. And imaginary numbers are numbers that have contained a letter, well, not a letter, but contain the number lowercase I. So like 3i, 4 plus 2i. These are imaginary numbers, all because of this symbol. If it has a real part and an imaginary part, again, it's called complex. When it ties a real number from this set to an imaginary number, it's called complex. Alright, the next set, number 2, is how do we simplify powers of I? Definition of I, imaginary number, comes from the fact that we cannot do square roots of negative numbers. Right now on your calculator, grab your calculator. Right now on your calculator, type in the square root of -1. When you do so, you'll notice on your screen it says non-real answer. If it's non-real, that means it's not real. That means it's imaginary. So any number that's a negative underneath a square root, we won't be able to give a real number answer for, and that's where the I numbers, imaginary numbers, comes into play. I squared is taking this and squaring it. And this is also an important one that we're going to have to memorize. So when I take an imaginary number and I square it, the answer to it actually is a nice whole number, or a nice integer, -1. So it is real. When I take an imaginary number, I, and square it, it becomes -1. So anytime you're doing a problem in this unit and in the future, when you see this math symbol, you can automatically substitute -1 in its place. I to the third is the same thing as I to the second times I to the first. Well, I to the third, or I to the second, I should say, is the same thing as -1 from the step above. And then I, we're just going to drop I down instead of writing it as a radical. I'm just going to leave it in terms of an imaginary number. And so the answer to I to the third is -1I. Okay, let's keep increasing the power. What about I to the fourth? Well, I to the fourth is the same thing mathematically as I to the second times I to the second. And recall that the rules you learned in the past for multiplication was if I had the same variable, I added the powers. Well, this isn't necessarily a variable. It is a letter of the alphabet, but it's not a variable. It's an imaginary number. But the good news is, imaginary numbers, we can use the same rules as we have with variables. And so when I see I to the second times I to the second, I'm allowed to add the powers and call it I to the fourth. I'm just going in reverse order. So when you see I to the fourth, you can think of it like this, split it up into factors. I squared is equal to -1. So this problem becomes -1 times -1. And that answer is just 1. So here's a second time that we have an imagined power of I, basically, that actually turned out to be a nice real number. And this one's a whole number. Okay, I the fifth. Well, I the fifth can be written as I the fourth times I the first. We already know that I the fourth is 1, but when we get to larger problems, powers that are a lot larger than 5, here's the game plan. You need to break it up in terms of get as close as you can to this value, and I did that, 4 and 1. The next thing you want to do is take like the I the fourth and write it as I to the second, and instead of writing it down twice, you actually can use the shortcut of using a big power of 2 at the top. So I squared, quantity squared, times I to the first. Well, I squared, again, the one that's really, really important, is equal to -1. So every time I see this symbol, I substitute. Well, -1 quantity squared is the same thing as 1I. And so right now, I have the answer for I the fifth as 1I. And I did have to show several steps, and that's what happens when you get, like I said, the higher powers. Okay, and we could keep going on this to infinity. But let me show you one that's a little higher so we can understand the concept. Let's say I gave you I to the 100th, and we don't have a list from between 6 and 99. So the first thing you want to do is you want to ask yourself, we always want to try to write it in terms of I squared. Basically, will 2 divide into 100? And if it will, if it's even, it should, then it's easier if you'll write this problem in terms of I squared. So I squared raised to something is going to be the same as 100. 2 times something is 100, and that's going to be 50. Okay, next you're going to substitute -1 in place of the I squared. And then if you need to on your calculator, because I'm definitely not going to write -1 out 50 times and see what happens, but you can think of it in terms of if I did do that and I wrote -1 out 50 times, every pair, every 2 would give me a +1. -1 times -1 is +1. So imagine me writing out 50 -1s, and there would be like 25 pairs of those. If this is even, then -1 raised to the 50th is going to be a positive value, a +1. Like I said before, you also can use your calculator and do parentheses -1 raised to the 50th. Just make sure if you are choosing to use the calculator that you use the parentheses around that number. Alright, let's try another one. Let's do I to the 7005. It's a huge power, 7005. So what we want to do right now is we want to ask ourselves, will 2 divide into 7005? Well, 7005 is not an even number. So what we're going to do is we're going to write it as close as we can. We're going to write it in terms of a power that is even. The closest I can get to 7005 without going over is 7004. However, this is not the same as this. So now I have to say, I've got 7004 I's. How many more do I need? I need 1 more. Please remember again that when you're multiplying, you add powers, so this plus this should make sense as to why it's equivalent. Next, you're going to focus on the even power. You're going to write I to the 7004 as I to the 2nd, because 2 goes into all even numbers, raised to the blank. And so you're going to take your calculator if you need to, divide 7004 by 2, and you'll see that you have 3502 left. That is the power that's going to go right here. You always want to check mentally in your head to make sure that this is making sense. Again, when you have a number or a letter raised to a power and then raised to another power, that's the power rule. Power rule says you multiply these together. So 2 times 3502 equals this amount. Then we're going to drop down this term here. Alright, obviously it's not simplified, so now I'm going to look inside and see that I squared, and I squared is always equal to -1. And I'm going to drop my power down, kind of copy everything down here, and then simplify. Imagine me writing -1 out 3,502 times. This is even now, so every -1 raised to an even power is always positive. And then you can drop your I down beside of it. 1 times I is 1I. Okay, so what I would do is I would definitely, for sure, memorize, let me grab this. I would definitely memorize these two. Like, make sure you know those two. This one you're going to use the most. And then when I give you a I raised to a power, your job is to break it up into factors, but your real goal is to see if you can get it in terms of I squared, since we know I squared is equal to a real number, and we're used to working with real numbers. So that's concept 2. Learning target 1 is just basically getting used to what an imaginary number looks like. Again, it has the lowercase I beside of it. It also can have like a real number in front of it or behind it being added or subtracted. That's called complex, and here's the form. And secondly, just knowing how to take these powers, or this imaginary number, raising it to powers and trying to simplify to get the best answer. Okay, learning target 3, how do we graph complex numbers? This one's super easy. If you'll follow these two statements, you're going to plot the real number on the x-axis. So here's the x-axis. You're going to plot the imaginary part on the y-axis. So we've got an imaginary axis, if you will, and a real axis. So here's the real, and here is the imaginary. Alright, let's take a look at example number 1. We are graphing -5 plus 3i. In this problem, we can see that this is a real number. We definitely know where -5 is on a number line, for example, so that's real. But the 3i is the imaginary part. Because there is a plus sign between those two, and because these are totally different types of numbers and unlike terms, we obviously cannot add -5 to 3i. Okay, so we got a real number and we got an imaginary number. Remember, according to that first slide, they're in different worlds, different boxes. And so if you can't combine them, you call this a complex number. You're going to plot the real number on the x-axis. So you're going to go to -5 on the x-axis. 1, 2, 3, 4, 5. You're going to go to, this is 3i, and it's actually a positive 3. So after you move left 5, and get back to where I was, you're then going to, on the imaginary axis, go to 3. So here's 3, and here's -5. And you're going to find where they intersect. So this is the location for -5 plus 3i. And just so I can refer to it faster, I'm going to call this point A, and that way I can put an A over here. So this is the graph of -5 plus 3a. Real part, -5. Imaginary part has a 3 in front of the I, so it's positive 3, means to move up. Very similar to how we plot ordered pairs in a regular basis, or on a regular basis. Number 2, same deal. We're going to graph 6i, but this time I notice it doesn't have a real part. So if I want to make it look like the other one, I can add 0 to it. Adding 0 to something never changes it, of course. Here's my real part now. Here's my imaginary part. And then I just plot. Okay, so let's go to real first. Real first on the x-axis, 0. Stay where you are. Okay, let's call this one point B, by the way. And then the 6 in front of the I is positive 6, meaning go up 6. And that location is going to be where your B is. Okay, so it's as easy as that. Plot the real number on the x-axis, imaginary number on the y-axis, figure out where they intersect, find your location, and label it, making sure we understand which point goes with which problem. Okay, learning target 4. How do we simplify radicals with I? Back when we were doing quadratic formula in the last unit, remember the discriminant was b squared minus 4ac. That was the number underneath the radical. That number could either be positive, negative, or 0. If it was negative, or if it were negative, I told you at the time to just stop there. Don't work the problem because I had not taught you the imaginary number unit. Well, now this is going to help us understand what to do in those situations. So, again, just a quick reminder, taking your calculator right now, I want you to type in the square root of -25. Okay, as you do, on your screen you should see non-real answer. So there is no number times itself that would ever give you back a negative 25. No number times itself, no real number times itself will ever give you back a negative 25. So your job is to simplify a radical with a negative. This is what you'll always do. When you have a negative number and you know that the answer is not, your calculator is not helping you to find the real answer, you pretty much know it's going to be imaginary. And so your answer is going to have an I in it, but this is how you'll work it out. You'll always factor out a negative 1. So whatever this is, you'll say negative 1 times that number. Negative 1 times positive 25 is still negative 25. So I've just basically written it as 2 factors. Next step, we know that 25 is a perfect square from the last unit. We know that this one's going to work nicely. We also know from learning in this section that when we see the square root of a negative 1, then it's the same thing as I. And so we're going to take those two pieces and tie them together. Okay, let's do the real part first. The square root of 25 comes out as a 5. And then you're kind of left with this. And then the next step you would do is, well, the square root of negative 1 is I. And there's a 5 in front, so it's just 5i. And you actually can skip this step. You can just say the square root of 25 is 5, the square root of negative 1 is I, so it's 5i. Now let me show you why it works very quickly so you can see like the math behind it. Remember that a square root means, again, what number times itself can give me negative 25 back. I just got the answer of 5i. So that means 5i times itself. Let's see what happens. 5 times 5 is 25. I times I, again, power rule or product rule, works with imaginary numbers as well. And that's a good thing. So you're going to add the powers when you're multiplying, and you get I the second. We're trying to get back to negative 25. 25i squared is what I'm seeing right now, but remember, every time you see I squared, I need you to change it over to what it's equal to, and that is negative 1. And so what we have left is 25 times negative 1, which is negative 25. And so it does work. That's the same thing I had when I started the problem. Alright, let's try number 2. Question 2 has the square root of negative 18. Again, if I took time to type this in a calculator, my calculator would not be able to give me a real number answer. So the first thing I do is I factor out this negative 1. Call it negative 1 times positive 18. I'm only doing that because I know that this piece right here is the definition of an imaginary number. Next, I'm focused on the 18. Is 18 a perfect square? So we're back to what we did in the last unit. Looking at those perfect squares, will 4 divide into 18? First of all, is 18 a perfect square? It's not in that list. So then you find the biggest perfect square that divides into 18 nicely. So let's break this down further. You're going to drop your negative 1 down. We'll come back to that. You're now going to write 18 as the biggest factor perfect square that goes into it. 9 would be the biggest one, so it's 9 times 2. And then you pause for a minute and you make sure that this problem you've just written is exactly the same as the original. Negative 1 times 9 times 2 is negative 18. Looking at these three numbers, this one I've underlined in green is imaginary. This one I've underlined in red is going to be a real number. And it's going to work out nicely because 9 is a perfect square, and then 2 is going to have to stay underneath the radical. So, tying it into things we've already done, you're going to say the square root of 9 is 3. You're going to put that outside or in front of the radical. The square root of negative 1 is the definition of imaginary numbers, which is what we're learning today. And then the 2 is going to stay underneath. the radical. And so this is the best answer. This is simplified radical form. Alright, let's go to number 3. Number 3 says the square root of negative 11. I see that negative again. I cannot think of a number times itself that gives me a negative 11, so the first step always is to factor out negative 1. That way you force this number to be positive. Then you think, okay, I've got an 11 underneath a square root symbol. Is the square root of 11 a nice whole number? In other words, is 11 a perfect square? And the answer is no. So then I look at my list and I try to find a perfect square that goes into 11. 4 does not divide into 11 nicely. 9 does not either. So that means 11 cannot be simplified. It would be like a messy decimal. So the only thing I really can do to finish this problem is at least take out the square root of negative 1, turn it into an I, which again, that's what it stands for, and then leave the 11 underneath the radical, leave it alone. And so the answer would be I times the square root of 11. Okay. Alright, so we're going to pause there on this set of notes. This was part 1 of section 4A, complex numbers. Remember that means numbers that have a real and imaginary part. We looked at how to simplify powers of I, how to graph complex numbers, and also how to simplify radicals with the answers with I.